We're back. We're finishing up assessing normality. These are making me look crazy. Assessing normality by investigating normal probability plots. So if you haven't watched assessing normality yet, you'll want to go back and watch that video and then come and do normal probability plots. So we discussed at the very end of our assessing normality worksheet that we have the option to go through on a data set and determine if it is close to normal or approximately normal by checking conditions or characteristics. So we can check shape, center, and spread. If they meet certain conditions like their shape symmetric, unimodal, bell-shaped, mean is approximately equal to median, and most of the data is within 3 standard deviations of the mean. If it's meeting those conditions, then you can say that it is close to normal or approximately normal. So you can do all of this work, or you can construct a normal probability plot. And if your normal probability plot is approximately linear, then you can say your data set is approximately normal. That is what we are looking at on this worksheet. So if a normal probability plot, so you can abbreviate that as NPP, and this is basically what I just said. So NPP, if that is approximately linear, then the distribution is approximately normal. So to construct a normal probability plot, you arrange your data values from least to greatest, you determine the percentile for each observation, you find the z-score for each percentile using the z-table, and then you plot each value against its z-score. So for our refrigerator data, that's not our refrigerator data. For our refrigerator data, let's look at the lowest value. So the lowest value is 12.9. So I'm going to find the z-score for that. 12.9 minus 15.825 divided by 1.22. I need to label that z or I would have missed points on this problem. 12.9 minus 15.825, I typed in the wrong thing, divided by 1.22 gives us a z value of negative 2.40. So what you're seeing here on the normal probability plot is a usable capacity of 12.9 and a z-score of a little bit less than negative 2. I think the difference between mine and theirs is, I bet you they calculated this with a different standard deviation, which is something that we can get into later, but it's pretty close. So what they're saying is you go through, oh wait, I know what the difference is. I'm supposed to find its percentile and then change that percentile, use the z-score from that percentile. So this is not what we're doing there. Sorry about that. So I'm going to say that one more time. Where this comes from is they calculate the percentile for 12.19. So that percentile is 1 out of 36. Which is 0.02, and then they go inside the normal table and find that area. So it's 0.278. 0.278. 0 to 6. I think that's as close as, 0 to, nope, we need to be even closer than that. 0.274. That's how many away? 0.274 away. This one's 3 away. So it looks like it's negative 1.91. And that actually looks like negative 1.91. I'm sorry if you're dying right now. So the percentile for 12.9 is 0.0278, which matches a z-score of negative 191. So you do that for every single point. You find the percentile, then you go in your table, find the area in the table that matches that percentile, and that is the z-score. Holy moly, I think that took 5 minutes, and you guys are probably so annoyed with me right now. But the good news is our calculator will do all of that work for us. So instead of having to go through and find the percentile for every observation, then find the z that matches it, we just plug everything into our calculator. So not only can you use your normal probability plot to determine if the shape is normal, you can also determine if it's skewed. So the normal probability plot tells you about the shape in general. So if the points are flatter on the right side, the data is right skewed. And we'll go through this in the pictures below. If the points are flatter on the left side, the data is left skewed. And if the points are approximately linear, the data is approximately linear. So let's look at this first normal probability plot. You want to look at where the points flatten out. And when we say flat, what we're referring to is them being horizontal. So we have two parts to this graph. We have this part of the graph that is very steep, and then we have this part of the graph that is much less steep. So I'm going to mark this part of the graph because this is the flatter part. So I'm just using a random C card that I have laying around. So if you break this up into two different portions, you can see you have two distinctly different slopes here. This green one is steeper. This blue one is flatter. This is the right side of your graph. This is the left side of your graph. So this means that this data set is right skewed, which makes sense to me because it kind of looks like these points on the right side are dragging out away from the rest of the data. So this is not approximately normal. This would be right skewed. So this guy, we have this section, this middle one, where the right-hand side is almost vertical. And the left-hand side is the flatter side this time. So if I want to mark this guy, doesn't got to be perfect, but in my estimation, it is flatter on the left side. So this is your left side. This is flatter than this part right here. This part is steep. So we would say this one is left skewed. left skewed. And you can see you have some, it's pulling out to the left. And then this last one is a really good visual of an approximately linear normal probability plot. So this guy is approximately normal. So let's look at these graphs. We should know all the names of these graphs. This is a normal probability plot. Stem, histogram, box, dot plot. Which of these is the least useful for assessing normality? Which is the least useful for assessing normality? Well, the most useful is the linear probability plot. What is the shape of this data set? You figure out that shape without me. What is the shape of that data set in this normal probability plot? So this guy is right skewed. This guy, the stem and leaf, definitely right skewed. The histogram, right skewed. Maybe that might be roughly symmetric. I'm not 100% sure on this guy. Dot plot, right skewed. Box plot, he's looking symmetric, but we have to keep in mind that on a box plot, what you can't see are gaps, clusters, and modes. What you cannot see on a box plot are gaps, clusters, and modes. So the least useful is the box plot. The least useful is the box plot because we cannot see characteristics like gaps, clusters, modes. And that's a great review for your comprehensive exam coming up. So personally, I think that the NPP is the most useful and the box plot is the least useful. Okay, we're almost there. We have 2 questions. Number 1, the following normal probability plot shows the distribution of points scored for the 551 players in the 2011-2012 NBA season. If the distribution of points was displayed in a histogram, what would be the best description of the histogram shape? So you want to use this NPP to determine, is it approximately normal, right skewed, left skewed? So B and E are not options because we can tell what shape it is. Symmetric but not approximately normal, that's not an option. It's either right skewed, left skewed, or approximately normal. Hopefully you have concluded that it is skewed right. Skewed right. If you mark it, this right-hand side is flatter, way flatter. This would be considered the left side, and he's almost vertical. Okay, our last problem is to construct the normal probability plot for this data set. This is the unemployment rate in the 50 states. So like this would be 7.4%. 7.4% of people are unemployed. So we're going to go to Stat 1. I have my data entered, so you should pause the video and enter yours. Okay, so to get your normal probability plot, you're going to go to second y equals. I always just use the plot that I have on. I've already forgotten what list mine are in though. 5. So I go to the plot that I have on. The normal probability plot is the last graph. It's the last graph in type. So I'm going to write that down. For my calculator, it's my, maybe I should write calculator. Last graph. So when it gives you type, it's your last graph. Mine was in list 5. And then you can change what your points look like. It can be like a little circle, a plus sign, a dot, or a baby dot. From here, we hit graph. Well, that's not helpful. So hit zoom, zoom stat. This is our graph. I would say that this guy is approximately normal. The shape of the unemployment rates is approximately normal. So biggest takeaway from this guy is knowing that in your calculator, to graph it, it is the last graph in the area where you get to select the graphs. Okay, that's it for normal probability plot. Your biggest takeaway from this is that you just want to make sure that you can look at a normal probability plot and decide the shape of a distribution, and then use your calculator to get a normal probability plot. So biggest takeaways, know what the shape is given a normal probability plot, and know how to get a probability plot from your calculator. If you did not understand what I was talking about when I was going through how you make one, that's totally fine. I wouldn't worry about that. Okay, that's it for assessing normality. Love you guys.